Okay. Hello and welcome to lecture 2 of EGR 335. My apologies in being late. I did not wake up this morning. I'm still asleep, actually. So, if I start talking about unicorns and pandas, it's just all just a lucid dream to me. So, what we've been talking about, well, what we're going to be talking about, we haven't talked about anything other than the course syllabus yet. Let's get into the meat of this course. And really what we need to do first off is have a review of what you really need to know bringing into this course. So this blue marker does not erase well. So I might end up looking like a Smurf at the end of this lecture. When it comes to digital circuits is kind of the whole point of this class. There is a big difference between a digital circuit and an analog circuit. And the difference between these is it comes in what they're used for. Analog circuits and analog components, really, they're used for power control. And the reason why power control is necessary is because you need to limit voltage, you need to limit current, you need to adjust voltage or current, and this is, analog components are really used to, they're used as filters, they're used in a lot of different applications for protecting components, transformers that change voltage values, change current. They're used in a lot of circuits for reducing the amount of current coming out of a circuit. There are a lot of analog components that are present in digital circuits because they're intended to reduce the current that comes out of your integrated chips. So analog components, they're just used for power, and that's really the purpose of them. On the other hand, digital components are not used for power. Now you could say, okay, well, you got a PWM controller, they're used for power. Awesome. They're usually not. An analog component, such as a switch, is sometimes used in place of these in combination with the digital components for power, but really what a digital component is used for is used for data transmission. Okay, now it's a common misconception that these two components exist on isolated circuits. In reality, they exist together. Anytime you break open any circuit, you're going to find resistors. Doesn't matter how digital or analog it is. Resistors are used to reduce current. They're used to force voltages. They're used to filter. So resistors are very common components, very cheap too. But they exist in a digital system. So analog components and digital components, they exist in each other's systems. And this is one way that a lot of digital circuitry has become very complex. It's because you don't just have this is an entirely digital system. You have to look at components for, okay, does this system need substantial power control? Usually the answer is yes. Filtration, all of these things. And then does this component need some element of information transfer? Again, usually the answer is yes. And so you have an amalgamation of both of these components. So typical examples of analog components would be resistors, capacitors, inductors. And I would also put switches in there too. Sometimes you could consider a transistor to be a switch, but I mean, sure, go ahead. You can put transistors in there as well. Digital components, this is anything that can go from anything that relies on Boolean logic. If you remember the difference between a digital signal has high and lows, whereas an analog signal experiences a range. Okay, and that's a digital signal. It transfers information by sequentially recognizing whether or not a gate is turned on or off. In an analog system, it transfers power based on an actual power value. Digital systems, at the moment, until we really invent quantum computing, digital systems only have 2 values. Analog systems can have an infinite number of values. So, big difference between the two. Anytime you're looking at a digital system, anytime you're looking at digital components, you're looking at things that transmit digital information. It's peaks of ons and offs. So this could be microcontrollers, this could be AND or NOT gates using Boolean logic. This can be anything from transistors also are digital components, so it kind of fit in both categories. So that's really where we're looking at when it comes to the difference between digital and analog. Digital's, while it does take more time. You could convey a lot of information in an analog signal. It actually takes more time to convey that same value in a digital system because you only have 2 values. Like let's say you're trying to convey the number 10,000. Well, in this system, you just have 10,000. Zoop! Or you have 10,000 divided by 100, and it's just 100. Or 10,000 divided by 1,000, and it's just 10. And that's all you need to know, is just 10. And then it converts from 10 to 10,000 just by multiplying by 1,000. That's easy on an analog system. On a digital system, to convey 10,000, you would probably need to have, let's say, because you've got, doing math in my head, you'd probably need something like 2 to the 8th, or even more, maybe even 2 to the 12th. You'd need 12 different digits, which means whereas this could be a single instance in time, this would require 12 different numbers, which means it would take 12 times as long to convey the same number as this would. So digital systems do take longer, but the beauty of this is that they're cleaner. You want to have a clean system because the difficulty with not having a clean system is that information is improperly transferred. Here, the difference between 10,000 and 9,000 could be it could be a 1 volt drop, which that could be caused by improper filtration. Or it could be caused by having a surge of power that goes through the surge protector that goes into the system. There are a number of things that can impact data transfer in an analog system. So while this is faster, this is much less accurate. This is far more accurate, it's just slower. Now the goal is eventually we want to make this have some of the speed aspects that an analog system has, but we are not there yet. We still have ways to go. So that's just a general overview of these. Now let's get into some of the topics we discussed in EGR 325, which was Intro to Electronics and Circuits. That's where a lot of this was introduced. We'll talk about binary math, and the whole reason why we're talking about binary math is because it's been a while, and trying to refresh those memories. So when it comes to, I'm just going to start drawing random lines. When it comes to binary math, let's say I have the number 946. Now 946 exists in a decimal system. This is literally portrayed as 6 times 10 to the 0th plus 4 times 10 to the 1st plus 9 times 10 to the 2nd. That is the way that this system works. It's an addition, addition, addition. Okay. Now this is in a decimal system, which means everything is base 10. In a binary system, we want to convey it in base 2 instead of base 10. And so what you end up having is, okay, if you write out your 2 tables, this is 2 to the 0th, 2 to the 1st, 2 to the 2nd, 2 to the 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, well, I was wrong. 13th, 14th, 16,384. Well, I don't need to go any higher than that. I went higher than I needed to. Okay, the idea is this number is equal to 512. So 946 is equal to 512, which 512 is, that leaves 434 left, plus 256. So that leaves, so it's 434 minus 256, and that leaves 8, 7, and 1. Okay, 178, so plus 128, and that leaves 50, plus 32, which leaves 18, plus 16, and that leaves 2, plus 2. Okay, now again, this is a much longer way of writing it out, but I just broke it down by picking the biggest number that was under this and then subtracting it from it. That's the way that I see digital math. And then you go back and look at it and say, okay, this is 2 to the 0th, 2 to the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th. Okay, so this is 2 to the 9th plus 2 to the 8th plus 2 to the 7th plus 2 to the 5th plus 2 to the 4th plus 2 to the 1st. Okay, so it would take 9 digits to be able to express this. So this would be 1, 1, 1, 0, 1, whoop, 1, 0, 0, 1. That's 946. Okay, so I have 1 in the 9th place, 1 in the 8th place, 1 in the 7th place, 1 in the 5th, 4th, and the 1st place. Every other digit is 0. You can also look at this by doing a divide by 2. So 946, you divide by 2, and the answer is, if it divides nicely, you get a 1. If it doesn't divide nicely, you get a 0. I think that's how it is. Something like that. Okay, so this becomes 473. Okay, so it did divide nicely by 2, and for that reason, then our 2 to the 0th place has a 0. Okay, so then we divide by 2 again. Okay, and then we end up with 286.5. This 0.5 means that our 2 to the first is a 1. So 286 divided by 2 is 143, which that means that our 2 to the second is a 0. Oh, I didn't include a 0th place. I guess that takes 10 numbers. Divided by 2 means this is 72.5. We take that 0.5, and that means our 2 to the third value is a 1. I'm getting a different number. Either that or I'm doing my math wrong. Which is entirely possible. But that's another way of doing it is the divide by 2 method, which I showed you. Really should have prepared this a little bit better. But I gotta figure out what's wrong here, because that's gonna bother me. I might have done my math over here wrong. In any case, that is another method. So you have your having everything add on or have everything divide by 2, and that creates your math, and that gives you a binary number. Okay. Now the idea behind binary numbers is that this binary number can itself be transmitted through a digital system. Now, if I wanted to transmit this 10-digit number through a system, what I could do is I could have 10 different wires, where this one is at 5 volts, this one's at 5 volts, 5 volts, 0 volts, 5 volts, 5 volts, 0, 0, 5, 0. You can do that. That's not a problem. I'll have all of that go into some integrated chip where it says, okay, if all of these are present, then that's the number 946. Okay? And that's really what digital systems do, is they take a series of bits, which that's what each of these are. They take a series of bits, put them together, and figure out what's being conveyed by those numbers. Okay, again, it's all used for data transmission. Okay. Now, let's say we were to try to convey the number 4. Or we're going to count to 4 in binary. We'll start with 0, 1, 2, 3, 4, 5, 6, 7, 8. I guess I counted 8. Okay, now each of these you'll notice this register changes by 1 every time. This register 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. It's repetitive. 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. This also repeats. This repeats every 2 digits. This repeats every 4 digits. This repeats every 8 digits. This repeats every 16 digits. Yeah, that is the pattern that comes with writing these numbers. So 2 to the first, second, third, fourth. That's however often it repeats. In a decimal system, you would say, if you were to write out, I don't know, 99 numbers, start with 0, 1, 2, 3, 4. This would repeat every 10 to the first numbers. So every 10 to the first, we would see another ones place. This repeats every 10 to the second numbers. So every 100 digits, you would see a repeat where it goes back to zeros. Okay? This one repeats every 10 to the third. So again, decimal system is just more efficient. It's faster than a binary system. We just, as of yet, haven't figured out the componentry to do integrated chips using this type of a system as opposed to this one. As soon as we do that, it's called quantum computing. Okay. But there is a different way of conveying numbers. This is just standard binary, but there's something that's called gray code. And the idea behind gray code is that in gray code, what you want is you don't want to have to change a number of numbers here. So I'm going to convey these as a series of dark and light blocks. Okay, so that gives me 4. Go ahead and break it off. There's 0, 1, 2, 3, 4, 5, 6, 7, and 8. Okay? If I were to just directly transcribe this over here, where a light box is equal to a 0 and a dark box is equal to a 1, then this becomes a 1, this becomes a 1, this becomes 2 1s, this becomes a 1, this, and then ultimately that. Okay, so I just took this image, brought it over here. Everywhere there was a 0 gets portrayed as a white box. Everywhere there is a 1 gets portrayed as a dark box. Okay, in this system, in order to add 1 to this system, I have to shut off this wire, turn on this wire simultaneously. If in that moment my clock register occurs while this is in the process of switching off and this is in the process of switching on, I receive an error because it will either jump to 0 or it'll jump to 3. Okay, so if this one turns on before this one shuts off and then the clock reads it, it reads as 3 instead of 2. If this one shuts off before this one turns on and then it reads it, it goes back and it reads 0. So if there is any small amount of error in these 3, we could read any number between 0 and 3 in the transition between 1 and 2. Okay? And that becomes troublesome, but it becomes even worse when it comes to a system like this right here. Okay? So in this system here, we have, this is 7 transitioning to 8. If all 3 of these stay on when this one is turned on, the number changes to 15. Okay? If this one turns off and all of these turn off, the number goes to 0. And you could have any combination of, if this one turns off, this one turns on, these two stay on. You could have any combination of numbers between 0 and 15 being read. If you have an error, or if you have a reading while some of these switches are turning off. Okay? And that can be hazardous. In a system like this, not knowing whether or not you are experiencing a number 0 to 15 is really bad. And it does require some knowledge of, well, you know, maybe, I mean, if you wanted to have that properly happen, so here I've got a graph, and I've got my data, my 4 data points, they're all high. Oh wait, nope, sorry. My 4th data point is low. Okay, this represents the number 7. So if a clock instance occurs right here, it would read the number 7. Okay, now this one then goes high while these 3 go low. And there's this transition period right here where if I have a clock signal that reads it, you do not know which of those signals are going to be on. Okay? We don't know which of these is going to be on and which one's going to be turned off at that moment, which is the reason why we could be reading anything from 0 to 15. And the larger our numbers get, the transition between this and this suddenly change. Okay, the transition between 15 and 16, you could be reading any number between 0 and 31. So the reason why we have gray code is because the transmission of this information needs to be cleaner. Okay, in gray code, what you have is you adjust how these are portrayed. So this is traditional binary, but traditional binary doesn't transition well. This right here, the transition 0 to 3, that's not a huge difference. If it reads a 0 or it accidentally reads a 3, that's great. This transition here, there's no difference at all. If there is an error, it accidentally reads the value it just was. If there's an error, or maybe it accidentally reads the value that it's going to be. But that's it. That's the only change. But anytime you have more than one switch changing at a time, pardon me, it does create the issue of what happens if an error is read too soon. So in digital systems, they will use gray code because it does reduce the error. If a time instance happens where it reads the value during a transition, you can guarantee it as one of two values. And I'll show you how. Okay, if a time error occurs in this transition here, it will either read a 0 or a 1. That's it. It will either read the value that it was, or it'll read the value that it's going to be. And the reason for that is you only have one wire changing values. It goes from all 4 of the wires having 0 volts to one of the wires having 5 volts and the other 3 wires being at 0 volts. Okay, so in this change, we only need to have one change at a time. What we're going to do is I'm going to represent this as 0, this will be 1, this will be 2, and this will be 3. Okay, now the moment I've done that, 0, 1, 2, 3, there is only one block transition in each of them. That's all. There isn't any big number changes. Now that said, once you introduce higher digits, then it's a switch from here to here. Oftentimes what you have to do to accommodate for that is you have to just switch on one at a time, or switch off one at a time. And that's the essence of what gray code is. I don't know if I'm doing gray code justice, but in each one of these, you only have one switch. That's all. It's not 2 switches, it's 1 switch. So trying to read the difference between these two, you either get this one or you get this one. If an error occurs, if you're reading on the transition, you only get one value. So here, if I were to read right here, I would either be getting a 1 or a 0. Similarly, down here, I would either be getting a 1 or a 2. So gray code adjusts how the numbers are portrayed. It adjusts the traditional binary representation to reduce error. And this is why gray code is seen in a lot of integrated chips and a lot of integrated circuits. The reason for it being that it wants to reduce the amount of error that is present in a system. Okay, so that is in effect what gray code is. You can look up the gray code values for numbers. I don't know, I don't think I portrayed it correctly, but I'm just teaching concepts. Okay, so one of the things that I've introduced today, as we've talked about these things, is what is an integrated chip? An integrated chip, in essence, chip or an IC is a series of gates that, when it receives signals, produce signals. Okay, so it's basically like a distribution hub. Information comes in, it's repackaged, and then the information comes out. An integrated chip will perform any number of features. It could be an AND. An AND gate is just an integrated chip. An OR gate is just an integrated chip. You have all of these different types of integrated chips that go all the way up to a microcontroller, something like a Raspberry Pi. Is just a very large integrated chip. It inputs signals, it outputs signals, and that's really all it does. Now, in the textbook, it does say that in an integrated chip, every Boolean algebra function can be broken down into a NAND. We'll get into this a little bit later. And basically what that ends up being is that an integrated chip just ends up being a whole sequence of NAND gates. And that's it. And there are some rules as to the way that gates work, but the purpose of an integrated chip is to input signals, process them, output signals. Okay? Go back to your 350 understanding. You have an input, you have an output. And this input could be any number of lines, and this output could be any number of lines. If you look at input-output for a digital number display, which I believe all of you had for your 325 final project. Here, in a number display, you have the numbers 0 through 16. There's 0, 1, 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 1, 1, 0. Okay, you have all of these signals all together. Oh, and then I think you have to have one more. You have all of these signals together, and these four signals will control 1, 2, 3, 4, 5, 6, 7. So you have 4 inputs and 7 outputs. And that's just for a digital number digit display. Okay? So you can have any number of inputs produce any number of outputs. And that's fine. That's what integrated chips are supposed to do. There is no limitation on, oh, well, I have to have the same number of inputs as outputs. No, you really don't. You can have more outputs than inputs. You can have more inputs than outputs. It just depends on the chip and how it works. For a lot of logic gates, like let's say it's an AND gate, you'll have 2 inputs and you'll have 1 output. For something like a JK flip-flop switch, you'll have 2 inputs, it'll go in, and then you'll have 2 outputs. And those 2 outputs will be Q and Q prime. Or, as some people put it, Q naught. Okay? You can have any number of inputs and outputs out of an integrated chip. It's just the idea is it's got to be able to do something with the inputs. And there has to be some kind of rationale for how the inputs get converted and get processed into an output. Okay? There has to be some conversion. We're going to talk a little bit more about Boolean algebra on Friday. I am also going to be talking a little bit more about, I have a few minutes. Well, let's talk a little bit about your project. My hands are blue. For your project, you are going to be designing an IoT sensor device. Now, I can't make any promises that we're going to be able to build this. I am scheduling everything possible to try to make it so that we can build one of these, because I think it'd be awesome. And I think it's really good experience for you to understand how it's constructed, drawn, everything. But in order for us to get there, we're going to have to start really early on in this semester. I don't want to reach the same situation I had last semester where I introduced the project too late and we weren't really able to do it very well. And then I ended up having to cancel a bunch of course material in order to make sure that we had enough time. I don't want to get to that point. So what we're doing instead is I'm giving it to you now, and you need to begin working on the background research, okay? IoT is an incredibly broad conversation topic. When it comes to talking IoT, you're talking anything that could go from building maintenance to safety to integration or optimization of systems. It just covers a broad spectrum. A lot of people use IoT for power, reducing power consumption and going towards a more green society. Some people use IoT for risk prevention systems, where it's monitoring things to make sure that they do not get too errant, and if they do become too errant, it sends signals to either shut down systems, alert somebody, bring them over, or a number of different applications. Okay, in order for me to feel really comfortable about you, the idea behind any engineering design process is you always have to do substantial background research before you really get into a project. And that's what we're doing right now. Right now you're sitting down, you're trying to figure out, what is IoT? What does it mean to be IoT? And once you understand what IoT is, the next step is understanding the different kinds of devices. And then the next step after that is picking a system that could be turned into an IoT device, or redesigning an existing IoT device. I don't have any problems if you want to build something that already exists. There's a huge marketplace right now for people who are designing IoT, because IoT specifications are very different from what a lot of traditional electrical systems are. And you'll find that in your research, because I'm forcing you to. I believe that's questions for next week's assignment. Okay, so for this Monday, I am expecting you to have a little short paper, should be less than a page, just discussing what is the breadth of what IoT is. And there are some questions that you need to answer there. But again, the goal for it is, I need to know that you've done enough research, that you understand IoT well enough that you could explain it to me, where I do understand it fairly well. And that's the goal of this project, this first assignment as a part of this project. Okay? All of the other assignments for this class have been posted already. And I guess we'll get back and continue this discussion oh yeah, we also need to talk about the design problem. We're going to talk about that on Friday. So I'll see you Friday. Have a good Wednesday, and peace out.